So thanks for the introduction, and I want to thank Francois and Marco for giving me the opportunity to talk. I'm very happy to be here and looking forward to sharing some of our results from within the last year or so on physics-compliant modeling and estimation of wireless channels that are parametrized by RISs. So we're very excited about this, and I hope, in this talk I can get across some of our excitement for this. So before I start, I just want to mention that obviously I've collaborated with a number of people that contributed to different parts of this work, so I want to mention them. And now I'll start, and I want to start by briefly, just on one slide, recalling the motivation for using RIS. So, I mean, we've talked about this in this workshop quite a bit, but I want to talk about it a little more on a more abstract level. So why is this smart radio environment actually a paradigm shift? So traditionally, the wireless engineer only controlled the input signals. Now with the RIS, you can control to some extent the propagation environment. And so this means, so the wireless channel, by the way, in my talk, I only consider linear radio environment. So it's a linear mapping from the input signals X to the output signals Y. And then we have this wireless channel H, which now depends on the RIS configuration. So yeah, this is what I just said. It's a linear mapping from X to Y, but the dependence of H on C is generally nonlinear. That's what comes out of the physics, and that's what I'll discuss in a lot of detail in this talk. And so then, the question is, what is this functional dependence? A lot of the signal processing literature assumes it's a linear dependence. So something like this, where you say, well, you have some line of sight path, and it's what they call cascaded channel models. This is at best an approximation of the physics of the problem. And that is, this nonlinearity fundamentally comes from coupling between RIS elements. There are two reasons for this coupling. There's proximity of RIS elements, but there's also a second component that has been largely overlooked, which is due to multipath propagation. So in some complicated radio environments, this can actually be even more important than the proximity-induced coupling. And so generally, the mapping from the RIS configuration C to the channel matrix H is nonlinear. So I want to start. If you look at the literature, there are essentially two approaches to physics-compliant modeling, and they are fully equivalent. They contain exactly the same physical constraints. So the first one, this is the one that I work most with because it's sort of more natural given my background in physics, is to describe the RIS elements as dipoles with tunable polarizability. So this is, in a way, a microscopic view because the polarizability is a local concept, meaning the polarizability of a dipole does not depend on what happens anywhere else within the radio environment. So that's what we mean by local. And so I'll explain this equation in a little more detail later. But this is essentially what, within the polarizability-based approach, the dependence of H on C looks like. C appears along the diagonal of a matrix that you invert, and then you take one block of that matrix, and that'll be your channel matrix. So that's one way to describe in a physics-compliant manner RIS-parametrized channels. And then there's the second way. Like I said, they're equivalent. They're just two equivalent ways of looking at the same thing. And so the second approach is to describe the RIS elements as auxiliary ports that you terminate with tunable load impedances. And this is more of a black box approach, where you say your radio environment is a black box that has these ports. And when you talk about impedances, impedance is fundamentally a non-local concept. So any entry of the impedance matrix depends on the entire radio environment. You change any tiny detail in the radio environment, in principle, all entries of the impedance matrix change. So that's what we mean by non-local. And so here you can see the full equation if you want to describe how the channel matrix depends on the RIS configuration within the impedance, tunable impedance based approach. And again, I'll say a little bit more about that later in my talk. But so just this basic comparison, like I said, I want to repeat this again, they're equivalent. So I'm not saying one is better than the other because they're equivalent, it's the same thing. But I think there are some things that you can, let's say, easier do based on one approach than on the other. So first of all, there's something in terms of mathematical complexity. So if you look at these two possible equations, the one on the left looks a little simpler. So in a way, it's more transparent. It's easier to see how the channel depends on the RIS configuration. And this complexity, I think also to some extent, obviously influences algorithmic complexity. What I think is more important is physical insight. So there are some physical insights that you can sort of straightforwardly deduce from the tunable polarizability-based approach, which I don't think you can that easily get from the impedance-based approach. And I'll elaborate on these in my talk, but the first one is understanding multi-bounce paths. And the second one is understanding the effect of moving entities. So I've said a few things that I think are positive about the polarizability-based approach. There's also something that is very nice about the impedance-based approach, which is when you're working with full wave simulations. So actually, in my group, we mainly try to do experiments. But when you work with full wave simulations, then you can actually get all the parameters that you need for the physics compliant model in the impedance-based approach with a single full wave simulation. So that's very convenient. All right. So there's this idea, well, I think there's like this sub-community of people interested in physics compliant modeling that is emerging, and Marco has been one of the pioneers and key contributors. So I want to give you a little bit of a taxonomy of how that seems useful to me to understand how this all fits together. And so I think, to my mind, the way in which you can best categorize things is in terms of the radio environment. So are you talking about a free space radio environment or a scattering radio environment? So actually, most of the literature is about the free space radio environment. And so there you can find this literature is all based on the impedance-based formulation. And there are different approaches that differ in simplifying assumptions that they make and converting, for example, to the scattering matrix rather than the impedance matrix. But in my talk, actually, I won't talk at all about the free space case. I'm more interested in the case when you have scattering objects in the radio environment. And so then you can think about what is the nature of these scattering objects. So the first possibility is that you think of these scattering objects as discrete dipoles. That is sort of a more academic, conceptual way of thinking about it. That's something we've looked at in terms of the polarizability-based approach, and Marco has looked at that with Vincenzo in terms of the impedance-based approach. So, like I said, this is for discrete dipole scatterers. But then, you know, I think for a lot of real-life radio environments, actually, the environment contains continuous objects, extended objects, dielectric objects. So here's some examples, like a factory, a plane, an indoor environment, a wireless network on chip. This is something we're interested in. I'll say a few words about this towards the end. And so in all of these cases, it's not really clear if you would want to describe the scattering environment really in terms of discrete dipoles. And so we've worked on physics compliant modeling for such scenarios, also in terms of the polarizability-based approach and in terms of the impedance-based approach. And so this is really what most of my presentation will focus on. So here's the outline of my talk. I'll start by introducing these compact physics compliant models of RIS-parametrized unknown complex radio environments. So this is important, that you don't really know the geometry and the material composition. Once I've explained this principle and how you can estimate the channel parameters, I'll move on to talking about some of the unique insights that you can get from the polarizability-based approach. Then I'll move on to something which now will sound to you as completely changing gears, but you'll see how that is highly related to this physics compliant modeling. So I'll show you how you can perform conjugate beamforming in an unknown radio environment without ever exchanging pilots. And finally, I'll say a few words about this method of estimating all the parameters of the impedance-based formulation in a single full wave simulation in an arbitrarily complex radio environment. All right, so I'll start with the first part. And this is the sort of prototypical experiment that we're considering in this first part. So this is a highly complicated radio environment, if you want. This is a metallic enclosure that has an irregular geometry. It's electrically large. And therein we have antennas, so that allow us to couple wave energy into the system with the transmitting antennas and out of the system with the receiving antennas. And then we have the RIS in there, which obviously allows us to impact the wireless channel. And so it's clear that there must be some function f that maps the RIS configuration C to the wireless channels H. But the question is, what is that function? Because in our setting, we do not know the geometry, we do not know the exact material composition, and even worse, like I already hinted at, this is actually a nonlinear function, so very hard to characterize. And the nonlinearity, like I said, comes from coupling due to proximity and reverberation. Okay, so the goal is now essentially to get this function for this highly complicated and essentially unknown radio environment so that we could describe our specific experiment. So, essentially calibrating the physical model to that specific setting. So here's the basis of our physics compliant model. This is in the polarizability-based approach, but everything that I tell you, you could also do with the impedance-based approach for this part. So the way we proceed is as follows. So we identify the primary wireless entities, which are the antennas and the RIS elements. Each of them we describe as a dipole. Each dipole is characterized by its polarizability. For the RIS elements, that polarizability is tunable. And then all of these dipoles are coupled to each other through background Green's functions. And here it's important to say background. Background means that these Green's functions, they depend in very sensitive manners on the complicated scattering environment. So if you change some detail of the scattering environment, these background Green's functions are going to be different. But just as a matter of writing down this model, we don't actually need to have closed form expressions for these background Green's functions. So here's our model. What we write down is this interaction matrix W, which has a local part, this diagonal matrix that contains inverse polarizabilities of the dipoles. And so remember, the RIS configuration is ultimately encoded into part of that diagonal, because when you change the RIS configuration, you're changing the polarizability of the dipoles representing the RIS elements. And then we have the non-local part, which contains the background Green's functions. And so we take these two together, we invert that interaction matrix, and we'll see in a few slides what that inversion, how that can be understood intuitively. And then one block of that inverted matrix is essentially the channel matrix. So that's the basis of the polarizability-based physics-compliant channel model. And I want to highlight, first of all, that the number of parameters here is completely independent of the complexity of the radio environment. So if this was free space or this highly complicated environment, it would be exactly the same number of parameters. And so what that also means is that there is no explicit need to describe this complex radio environment. We do not need to discretize it or anything. All that we need is to understand how it impacts these background Green's functions. And that's going to be essentially the question. Now we have this model, which is so far abstract. If we want this model to describe exactly this experiment, we'll have to figure out, we'll have to estimate the parameters of this model. So the polarizabilities and the background Green's functions. And so the way in which we do this is very traditional signal processing in a way. It's a very principled analytical model-based approach. And we do this just through gradient descent, in fact. For a bunch of random RIS configurations, we measure the corresponding channel matrix. And then through gradient descent, we figure out what must have been the parameters of our model, so the polarizabilities and the background Green's functions. And this works surprisingly well. So here you can see some comparison of predicted channel coefficients for unseen RIS configurations. So comparison of the ground truth and what our model predicts. We have introduced this metric to quantify the precision of our model, which is defined like a signal to noise ratio. And so if you compare it to benchmarks that you could think of. So first of all, a linear model that would sort of represent these cascaded channel models that are very common in signal processing. You see, the linear model is orders of magnitude worse. But that's not surprising because you understand that obviously if you have a nonlinear function, you try to approximate it with a linear function that can't work very well. But what is maybe more surprising is that the deep learning approach is also an order of magnitude worse than our physics compliant model, even though it's using orders of magnitude more parameters. We believe so we're using a fully connected neural network here, and we believe that is because this architecture is just fundamentally different from the recurrent scattering that is physically happening. You know, you only have feed forward, as the name says, and not the recurrent nature. So one thing that is interesting to look at is what accuracy does the model achieve as a function of the number of available calibration measurements. And one striking feature in this plot is that there is this seemingly phase transition for the physics compliant model. And that happens earlier the more channels you're trying to estimate. And that makes sense because the physics compliant model understands how different channels are related to each other. And so if you ask it to predict more channels, it'll actually need fewer examples. And that's, of course, very attractive if you think about, you know, these trends towards massive MIMO using more and more antennas. You'll have to estimate a lot of channels. And, you know, essentially, the more channels you have to estimate, the fewer calibration measurements you need to make. So that's very nice. So far, actually, I think you've already seen that there's a number of 10x advantages of using physics compliant channel estimation in terms of accuracy, in terms of compactness, or number of parameters, in terms of the number of required calibration examples, and also the scaling with the number of channels. So all of this suggests that using physics-compliant channel estimation could be a very frugal approach to controlling wireless channels with RIS. And as you'll see in a minute, there's yet a lot more benefits which come from naturally built-in constraints in these physics-compliant models. But before that, I just want to mention, so this is obviously a very academic setup, but we also tested this in an actual indoor environment, and it works just as well. Okay, so the first thing that we can go beyond what I just told you relates to phase information. So it turns out that actually we can estimate all the parameters of our model without ever measuring phase. So just based on intensity measurements, we can calibrate a model that will predict both amplitudes and phases of all the channel coefficients as a function of the RIS configuration with extremely high accuracy, you know, orders of magnitude better than what the neural network can do with phase information and many more parameters. So why is that? Well, fundamentally, it comes from the mathematical structure of the physical model. There are constraints built into this model that mean that if the model is correctly predicting amplitudes, then it must also be correctly predicting phases. And so this is very nice because now we can think about non-coherent end-to-end channel estimation in cases parameterized by RISs without ever measuring phase. And obviously that makes the hardware much easier because if you don't have to measure phase, you don't have to worry about synchronization and so on. Now, obviously phase retrieval is an established, you know, sub-community in signal processing, but the usual problems that are studied in phase retrieval are involving linear mappings. Whereas here, obviously, the function, the mapping that we're looking at is highly nonlinear. Like I explained, you have this matrix inversion and so on. So it's much more complicated, but it's actually also that complication that makes life easy for us because it involves all these constraints in the mathematical structure of the problem. Okay, so we did this in the experiment that I just showed you, and then we can go on to perform coherent wave control using the RIS and controlling the coherent wavefronts that are radiated by the transmitting antennas without ever having measured phase. So here's some examples of conjugate beamforming, coherent absorption, QPSK backscatter communications, all of those performed without ever having measured phase. And you see the performance is just as if we had known the ground truth channels. So this is the sort of phase retrieval capability of physics compliant channel estimation, but we can go one step further still. So we can actually hide an entire plug of the scattering matrix from our calibration data. And then we can ask our model to predict the channel coefficients that we've never measured. And what you see is that the model actually still correctly predict how these channels that we've in this configuration up to a constant offset, which, if it matters in some applications, you can calibrate out with a single measurement. And so now again, we can perform coherent wave control based on, or partially based on, channels that we've never measured. And it works just as well as knowing the ground truth. All right, so that was the first part of my talk. So that was introducing these compact physics compliant models of RIS-parametrized unknown complex radio environments. Now, I want to discuss some insights that we can get from these models, particularly from those based on the polarizability-based approach. So for that, now I will move to this scenario that I mentioned earlier, which is a little more academic, where you consider a radio environment that is actually just comprising dipoles in free space. So this is what you can see here. We have created some scattering enclosure with a couple of environmental dipoles. This is a 2D simulation. This is actually from the first time we started studying these physics compliant models, and the code is available online if you're interested in playing with it. So if we're using this sort of explicit description of the radio environment, then our interaction matrix is essentially a 4x4 block matrix. So we have blocks corresponding to transmitters, receivers, RIS elements, and the scattering environment, so T, R, S, and E. And so basically, this is a reminder of what I said earlier. You have this interaction matrix, you invert it, and then one block, the block RT, will be essentially your channel matrix. And the RIS configuration, just again to remind you, appears along the diagonal of the block WSS. All right, so now if we want to get some more physical insight into what does this matrix inversion actually mean, we'll take the following approach. We'll apply the block matrix inversion combined with a power series expansion multiple times in a hierarchical order to basically figure out what you see in this schematic in a more mathematical form. And so I'll go over this pretty quickly. So the first step is to just consider a transmit array in free space. And so basically you have this inversion, which you can write as an infinite sum of matrix powers. And some of you might recognize this as the Born series. Then we go to the next step. We have a transmit and a receive array in free space. And so again, we can do similar mathematical procedure, and we wind up with a second infinite series. This has a little different structure, so we call this a Born-like series. And you see that actually the other series is nested into this one. So you see there's a WSS inverse, WTT inverse, WRR inverse that appears, that itself is the infinite series from the first case. Then we can add the RIS, and then eventually we can also add the scattering environment. And so, well, there's a lot of mathematical detail that I won't discuss now in this presentation, but basically the key point is, well, the first key point is that this matrix inversion very compactly captures all of these infinite numbers of multi-bounce paths that you can imagine that can arise in such a radio environment. So here, the key points, and they actually help us to relate this physics compliant model to the very widespread cascaded models. So first of all, the physics compliant model, at least in its polarizability based formulation, can be understood as a sum of nested infinite series, Born series and Born-like series. In these series, the kth term physically represents paths that involve k bounces, either between RIS elements or between wireless entities. And so then you understand that the common cascaded models, they obviously truncate these infinite series at linear order. So after the first or second term respectively. And so now we can actually also think about what physical parameters determine the importance of this truncation error. And so we can actually start trying to think about in certain scenarios, does it make sense to use, or how bad is it using these cascaded channel models? So first of all, in terms of the proximity-induced couplings, if we want to just focus on proximity-induced coupling, we'll place ourselves in a free space radio environment. So this is an anechoic chamber where there are no reflections. And And so you can figure this out from the maths, but it's also quite intuitive that the importance of proximity-induced coupling depends on three factors: the scattering cross-section of the RIS elements, the number of RIS elements, and their spatial arrangement. So here, for example, some measurements where you can see that as the number of RIS elements increases, the accuracy metric of a linear approximation deteriorates because the coupling gets more important. We can also then start thinking about what determines the importance of reverberation-induced coupling. So this will be, first of all, reverberation time. So the longer the wave dwells in this radio environment, the more it'll create coupling, because basically it'll bounce around, and along a given trajectory, it'll encounter multiple RIS elements. And then the second factor is also the dominance of the RIS in the radio environment. This is a little vague concept, but it relates to where you place the RIS and so on. There's no generic mathematical formulation for this, but we did some experiments in different reverberation chambers of different sizes, and we see that qualitatively they confirm what we expect, that the linearity metric gets much lower in these reverberant environments. All right, and I'll just say a few more words about other things that you can understand. And now that I've sort of explained the physical intuition behind why the wireless channel depends nonlinearly on the RIS configuration. So one thing that you could do is consider using the structural nonlinearity for physical neural networks. So you would encode your input data into the RIS configuration, just as you would do in backscatter communications. And then your output would be defined as, well, some parts of the transfer function. So like, the intensity at certain frequencies. So I want to stress what I call input and output here is not wave input and wave output. It is, here we say we define the RIS configuration as the input, and we define the intensity of the transfer function as the output. And then that'll be a nonlinear mapping, even though we are operating in a linear wave system. All right, so this is something that we considered recently in a project where we're actually interested in how you can train these physical neural networks. So I won't go into this in this presentation, but we're actually interested here in backpropagation-free training, so it's some kind of contrastive learning. And one of the physical platforms that we considered was this RIS-parametrized complex radio environment. One other thing that I want to mention is, so we were wondering if you could use a RIS inside a reverberation chamber to emulate wireless channels. So for example, could you emulate adjustable Ricean channels? And then by basically sweeping the RIS through random configurations, and if you use fewer elements, then you would have a different K factor and so on. So that seems fairly simple at first sight, but it actually turns out that there's unsteered wave energy in this setting that is quite hard to get rid of. And based on the model, it's actually quite clear that there must be two qualitatively distinct origins of unsteered wave energy. First of all, of course, you have rays that never encounter the RIS, so they will be independent of whatever RIS configuration you pick. But they're also, part of the wave energy that travels along paths that do encounter the RIS is actually also not influenced by the RIS configuration, which in our model, you can understand by the fact that the polarizabilities corresponding to the different RIS states don't average to 0. Or in more antenna language, what you would say is the structural scattering of this RIS is non-zero. And by the way, longer reverberation times, they diminish both of these effects. And now, so this was what I told you so far was about understanding basically multi-bounce paths using this physics-compliant model, and in particular using the polarizability-based approach. And now I want to show you one other thing that one other unique insight that I believe you can get from the polarizability-based approach that is not, as far as I can tell, easy to get from the impedance-based approach. And so this is something we came across when we try to use these physics-compliant models efficiently. So I told you basically that you have to do this matrix inversion in order to get the wireless channel matrix. If you have to do that once, then that's okay. But usually, in fact, if you think about some optimization, and usually that's what we want to do if we have a RIS, then you have to compute many channel realizations for example, different RIS configurations. And so you might have to do this inversion many times, which might seem scary in terms of computational complexity. And so we're interested in looking at how you can use physics-compliant models in a numerically efficient manner. So the first part of that is what I already mentioned in the previous, in the first part of my talk, was to always work in a reduced basis of primary entities. So basically, you only want to explicitly represent antennas and RIS elements, and the environment should always go into the coupling between these primary entities, which you can also understand this just as a block matrix inversion. But then the sort of the new part on this slide for this talk is how you efficiently update previously computed channel realizations. And so here, actually, this Woodbury identity from well-known linear algebra is very relevant because you can use it to understand how you should update the channel matrix in case you change the configuration of the RIS element. So every RIS element essentially yields a rank 1 update of the channel matrix. So that, by the way, if you change the RIS configuration, recall that you're changing one element of the diagonal of that interaction matrix. But there's also the case of a displacement of entities. And so if you have a displacement, what is happening is that you're changing one column and one row of this interaction matrix, except for the diagonal entry. And so a displacement of a wireless entity must yield a rank 2 update of the channel matrix. This is something that is fairly straightforward in this polarizability-based approach, whereas if you were looking at the impedance-based approach, you could not arrive at that conclusion because all entries of the impedance matrix would change if you have motion of an entity. All right, and we'll get back to these conclusions in a minute. So, because now I'll talk about this conjugate beamforming without ever exchanging pilot signals. Sounds like a completely different topic, but you'll see that it is highly related to the previous slide. So, you know, you imagine you're in a highly complicated unknown radio environment. You have some user equipment. You want to focus on that user equipment, but without ever exchanging pilots. So if you want to focus like conjugate beamforming, obviously you have to know the channel from your transmitters to that user equipment. But how are you going to find them without ever exchanging pilot signals? Obviously, if you could do that, that would be great, right? Because you could think about applications in communications, in wireless power transfer, sensing, and so on. And by the way, this is not only relevant to wireless networks, but also in optics and so on, biomedical imaging. So one possible solution is that if your target, your user equipment, is perturbing the radio environment, then that'll change the channel matrix. So maybe you, based on that change, you could figure out how you should be focusing on that user equipment. And there are two types of perturbations that could originate from the target. The first one is a polarizability change, or in antenna language, a change of load impedance. And this is actually quite common. So, you know, in RFID, in backscatter communication, RIS, obviously, wireless bioelectronics, cybersecurity, EW. So polarizability change is one possibility. Motion is another one. So in both cases, the channel matrix will change due to a perturbation induced by the target. And then, you know, the hope is that based on that change, you could figure out what are the channel coefficients from your transmitters to that user equipment. And, you know, so far, there are a couple of ideas around, at least in the wave physics community, related to this, but there hasn't really been a clear theoretical understanding of scattering in a target perturbed complex environment. And certainly there hasn't been any proof of performing this focusing optimally. So So, you know, if you want to focus, by the way, what this means is actually you don't have to find the channel, but you have to find something, you have to find a vector that is collinear with the transmission coefficients from the sources to the target. That's enough for perfect conjugate beamforming. And so there hasn't been any proof that what other papers found was actually optimal, and actually it was not. But using the physics compliant model, actually this is a super simple problem. So you realize that this target, you can think of it as just one RIS element. And so if we look at this interaction matrix again, so we have all the antennas. Here I have 7 antennas. And then you just have one RIS element, which is the target. I mean, in the mathematics, the target or RIS element is exactly the same. And so, and And so this is the model that I've discussed throughout my talk so far. You have this interaction matrix, you invert it, and then part of that is the scattering matrix or the channel matrix and so on. And so how does the polarizability change or motion impact the channel matrix? Well, this is what I just showed you a couple of slides ago. If the target changes its polarizability, so modulates its impedance, we have a rank 1 update, and if it moves, we have a rank 2 update. And so with just okay, so this is what I just said. So with just a little bit of linear algebra manipulations related to single value decompositions, we can actually figure out the vectors that are collinear with the transmission vector from the sources to the target. And so we did these experiments for the case of a polarizability change and also for the case of motion. And in our experiments, of course, we can actually measure the ground truth, so we can verify that we're getting this correctly. And you see it works perfectly. If we have good SNR, then we get a perfect conjugate beam farming on this target if it's either changing its polarizability or moving without ever exchanging pilots. And in the case of motion, and this is something that has not been appreciated in those few papers in the physics literature that I thought about related problems, is that you need at least 2 displacements of the target in order to figure out a vector that is collinear with the channel vector that you're looking for. And why is that? It's because the update of the channel matrix is of rank 2. So if you have 2 displacements, the vector that you're looking for is in both of these 2-dimensional spaces. So then you look for the intersection of these 2 spaces and you find the vector that you're looking for. And as you can see, this works nicely. And by the way, the same approach can also be used in case of a dynamic complex environment in order to optimally deliver, to optimize the time averaged power delivered to a target. All right. So now so throughout everything in my talk so far, I've talked about the. Okay, that's okay. Okay, I'll need less than that. Yeah, we're almost there. So throughout everything in my talk so far, I've mainly talked about the polarizability-based approach. In this very last part, I'll say just a few words about the impedance-based approach. And in particular, how you can estimate its parameters in a highly complicated setting using a full wave simulation. So the impedance-based approach, I'll just remind you very quickly, I've already mentioned this. You have an impedance matrix whose dimensions correspond to the number of antennas in your system, so transmitters and receivers. This is related to a scattering matrix. And if you have RIS elements, you consider them as additional auxiliary ports. So you have an augmented impedance matrix whose dimensions correspond to the number of antennas plus RIS elements. And then you terminate these auxiliary ports with tunable loads. And so you wind up again, that's the relation between the load impedances that you choose and the impedance matrix that you can actually measure with the antennas. And so basically, this augmented impedance matrix you can extract from a single full wave simulation, irrespective of the complexity of the radio environment. So like I told you, in my group, usually we try to do experiments, but there's this one topic that we're studying where experiments are not so easily done, which is wireless networks on chip. And in the interest of time, I won't discuss why we're interested in this, but I can answer questions if you have. But so this is a sort of typical wireless on chip environment. And you can see you have this metallic enclosure, you have dielectric layers. So it's a very complicated radio environment. But just by declaring the lumped elements, so that's why we want to study this in simulation, by the way, because doing experiments on this is not easily within reach. So in order to get the augmented impedance matrix in this case, we just declare the lumped elements as lumped ports in our full wave simulation. And then with a single full wave simulation, we get all the parameters that we need for the physics compliant model. And so in this case, we used this to perform over-the-air equalization. So this is a time domain approach. We want to make the impulse response look pulse-like despite the rich scattering. And so you can see that, first of all, the over-the-air equalization works. But we're doing all of this based on our model, and then we compare it to the ground truth, and the agreement is very good. All right. So with that, I'll wrap up. So I hope I managed to share some of our enthusiasm for these physics compliant models. I think that in terms of channel estimation, they enable very frugal approaches. There's some insights, especially from the polarizability-based approach that you can gain, which I think not the community is not fully aware of so far. And we can even apply it to problems that seem unrelated but are actually easily solved. So this conjugate beamforming without pilot exchange. And with that, I'm happy to take questions.
Wow, I have lots of questions.
All right,
so,
yeah.
First, basic question. Can you go back to the definition of W?
Sure.
And I understood the diagonal coefficients, but the G part, how do you acquire that? What do you need to measure? This I really
so the parameters of the polarizabilities and the background Queen's functions, and we're not assuming to know any of these a priori. So we do assume that we know our RIS design. We do not assume that we know the radio environment. We just estimate to a set.
So, and you said you do not need to measure the phase. You only measure the
that's right.
So, if I understand correctly, you need to set the RIS into all of its configurations.
Not all. I mean, all would be impossible, right? We have 100 elements or so. Okay. 2 to the power 100 wouldn't finish in this lifetime.
How many configurations do you need to test?
Yeah. Okay. So, well, I think this figure partially answers the question. In the case of using complex valued measurements, we did this we did this sort of a detailed study. You can see in the best case we needed 400. That's
400 configurations.
Yeah.
You need to test 400 configurations. It's huge.
Well, I mean, it depends on what are your standards. What precision you want to get. We were here very we were aiming for very high precision. Like 1% error maybe. If you're happy with 10% error, then you need fewer.
So this I guess answers my second question, which was what source of error in the physical CISO model? Is it noise only? Is it the number of measurements? Is it do you need true dipoles in your experiments? I try to understand what are the sources of error.
So the notion of dipole it's true. I didn't discuss this in too much detail, but it's a very interesting question. So what are actually the dipoles that when I say dipole, what do I mean? I don't mean a dipole antenna. So the dipole, in the case of the antenna, the dipole is actually the charge separation when you connect the coax cable to your antenna. And that is always electrically large, no matter how electrically large. It's always electrically small, no matter how electrically large your antenna is. So that's something that we saw when I did the conjugate beamforming without pilot exchange. I didn't discuss it in much detail, but no matter what size of antenna I used, it always worked because this the coax cable is always electrically small. And in terms of the RIS elements, what matters is not the size of the RIS element, but the size of the tunable lumped element. And so again, this is always, when you're using pin diodes, is always very small compared to the wavelengths. And so this always works very well.
So the sources of error are only noise and number of measurements. Is my understanding correct? There is a gap between the red cross and the circle, right?
Yes.
So what is the source of error? It's noise and limited measurements?
Yeah,
or there is something else?
Well, I mean, it's a parameter estimation problem, and you never have a guarantee of finding the global optimum, right? I mean, actually, there's a lot of ambiguity in this problem, but that helps us to find a decent solution easier.
Okay, so there is no requirements on the antennas or the unit cells. You said it's
well. So as long as you're using tunable lumped elements that are electrically small, this model should apply. So here we're mainly talking about like microwaves, millimeter waves. So most prototypes involve pin diodes, varactor diodes. So it's always electrically small tunable lumped elements. If we're moving to terahertz frequencies where you don't easily have pin diodes, and if you start using phase change materials and so on, and then you have electrically large things that are changing, then you need to adopt this model.
And last thing, and then I give the cube so to someone else. There is no requirements on the kind of phenomenon in the propagation, because here I see no absorption, sorry, only reflection, reverberation.
Oh, there's a lot of absorption. There's a lot of absorption. The walls are ohmic, they have a lot of ohmic losses. So actually here, the average transmission between the antennas is probably have 20 dB loss. There's a lot of absorption here. So, so maybe to answer your question, basically, the whole complexity of the radio environment is lumped into these background Green's function coefficients. Okay. So any coupling effects that you can think of, surface waves, propagating waves, absorption, all of that, I mean, all of that has an effect on these background Green's functions, and we just need the value in fact. You know, we don't need to have an analytical formula that says you have a wall here that'll impact the value in that way. We just want the value, and that we get from parameter estimation.
Actually, I do have a question.
Yeah.
So the configuration of the RIS in terms of its phase matrix, how is that going to change? And like, have you considered it in this study? How is it going to change with the position or of the object, or were you moving it in the room? Is it considering the imperfections of that?
Imperfections of what?
Well, that you're gonna have different losses at different phase angles.
Okay, yeah. So
and also near to far field transition, that sort of thing.
Okay, so I mean, so in terms of near field, far field, I mean, we're not making any assumption here. This obviously, it's all factored into these Green's functions. The Green function tells you basically what is the Green's function. It tells you if you have a dipole moment at position I, then what is the field induced at position J. And as long as you know that, you know, you don't need to worry about any of these assumptions, near field, far field, what kind of propagation and so on. It's just all in that value. But
yeah, but what I mean is that the RIS may not be able to configure itself to give that kind of field at this kind of position due to its physical limitations.
No, but we're not assuming that it's that the RIS has unlimited capabilities. No, we're assuming it's a binary RIS, so we have two possible states, which means that for every element we can choose between two polarizability values. Yeah. So yeah, there's no assumption that it's a magic RIS. And I think there was one other thing you mentioned that I wanted to comment. Oh yeah, so this study is for a static environment. So moving to dynamic environments is something that is, you know, left for future work currently. Of course, if you change a detail of the environment, then in principle all of the background Green's functions are changing, and so you should re-estimate them if you want to apply the model in the new realization.